Well, hello. Today we're going to discuss exponential functions, but before we do any of that, we are going to review some exponent rules that you've been using before. I'll just say rules of exponents. And I think I'm going to write down all of the ones that we're going to use so that they're listed in one spot rather than spreading them out, stating them as we use them. So I'll write them out first. And the first exponent rule you've used every time you've FOILed. Every time you've ever FOILed, you've used this rule. Anytime you say x times x is x squared. A to the m times a to the n. This is an m and an n exponent. We have exponents and we have bases. The a is what I'm using for the base. A to the m times a to the n is a to the m plus n. Every time you ever said x times x is x squared, you were using that rule. And you might think, well, wait a minute, there's no exponent here. Sure there is. X to the first times x to the first. So the first rule says to multiply like bases, you add the exponents. The second rule you've used every time you've canceled stuff like this. A to the m over a to the n. If you have the same base, to divide that, you subtract the exponents. And you've used it. Ex, for example, if we had something like this, x to the fifth over x squared. If you were reducing this fraction, x to the fifth over x squared, you could cancel two of the x's up here on top with these two x's there, and you would be left with a x to the third. In other words, you're subtracting the exponents. Okay? So anytime you've canceled variables like that, you were using the second rule of exponents. The third rule is a direct result of the second rule. I'll write it like this. Anything to the zero power. So this is our definition of a zero exponent. Anything to the zero power is 1. And sometimes people say, why is that? Well, it has to do with this second rule. If we're going to buy the x to the fifth over x squared is x cubed, then what would have happened if these two exponents had been the same thing? If we had had x to the fifth over x to the fifth, and we subtracted them, we'd get a 0. But anything over itself has to be what? Say why. Let me try to justify why. If we had a to the fifth over a to the fifth. Ooh, can y'all read those? Those are exponents of 5. I'm setting up a problem like Rule 2, but here the exponents are the same thing. Rule 2 says we can subtract those exponents. So that would get us a to the 0. But there's a fundamental property about division and about fractions. If you have the exact same thing on top and bottom on a fraction, what do those have to equal? So it has to be 1. So something over itself has to be 1. So looking at this, a to the 0 has to equal 1. Now that rule we'll be using right off when we start doing the problems. Once again, I'm going to state all of the exponent rules that you'll encounter in this course. That was the third one. The fourth one tells us how to raise one power to another, or in other words, how to get rid of parentheses. Generally in algebra, when you get rid of parentheses, you multiply, and that's true here. To get rid of these parentheses to raise one power to another, you're multiplying. For instance, if we had x to the third squared, what am I saying the answer would be here? How do you raise one power to another? What is Rule 4 saying? Multiply. So x to the third squared would be x to the sixth. And you could convince yourself of that by thinking of this as x cubed times x cubed. And then using Rule 1, you would add the exponents and still get x to the sixth. The main rules we're going to be starting off with are rules 3. I think 4 will pop up before the assignment's over. I'm not so sure you're going to see Rule 1 or 2 much today. But again, I wanted to state all the rules of exponents that you'll eventually see. Rule 5 is the formal definition of a negative exponent. A to the negative n power a negative exponent, watch the colors, that red negative means 1 over. So a to the negative n is 1 over a to the n. And this is something you might not have used any negative exponents in a long time. By the time we're through with the next few assignments, you'll be good with working with negative exponents. Suppose we were trying to simplify 5 to the negative 2 power. Well, what are some of the wrong answers? Some of the wrong answers would be maybe negative 25 or negative 10. It's not negative anything. A negative exponent means 1 over, so that red negative up here becomes the red 1 over, and then 5 squared. So 5 to the negative 2 power, it's not a negative answer, it's a fraction. What's my fraction going to be? 1 over 25? Rule 5 tells you how to simplify or how to work with a negative exponent when the base is just an integer, not a fraction. What the heck do I mean by that? Number 6, if we had this, the fraction a over b to the negative n power. Here's the definition of a negative exponent when the base is a fraction. A over b to the negative n is the same thing as b over a to the positive n. So just flip the fraction and drop the negative. I'm wondering if y'all can help me simplify this fraction. 4 over 5 to the negative 2 power. Did y'all hear that? You flip the fraction, and that makes the exponent positive. So it's now 5 over 4 to the 5 over 2 power. which we can simplify just by squaring the 5 and squaring the 4. What would that be? 25 over 16? We'll have several homework problems involving those two rules, negative exponents. And here's a rule that we stated when we were working with square root equations at the beginning of the semester. I'm defining what I mean by a fractional exponent. We've defined a zero exponent and negative exponents. What if we had the fractional exponent 1 over n? And this one we've stated this semester. A 1 over n exponent means nth root. Okay. 1 over n exponent means an nth root. For example, suppose we had this. 8, the number 8, raised to the 1/3 power. 1/3 exponent. Watching the colors, this 1/3 exponent means cube root. A 1/3 exponent is just another way of writing cube root. And so what is the cube root of 8? There's not a square root that we can easily find. It'd be a decimal number. But we can figure out a cube root. But 2? Yes. 2 times 2 times 2, is that 8? Yes. And then, once you've seen this, the 1 over n exponent, the natural thing to ask is, well, wait a minute. Suppose the top number wasn't a 1. Suppose we had the exponent m over n. Well, when you have an exponent m over n, the bottom number is the root. Just like over here, the 3, the bottom number was the root, the cube root. And the top number is the power. Suppose we wanted to figure out 4 to the 5 over 2 power. 4 to the 5/2 power. How would we simplify that? Exactly. Did y'all hear that? The top number's the power, the bottom number's the root. I suggest you do the root first because that'll get you smaller numbers. This bottom number here is a 2, so that means square root of 4. Notice with square roots, we don't have to write the little 2 right here. I guess if you want to, you can, but you don't have to. You say it. But like with cube roots, you've got to write the 3. Okay? So square root of 4, then raise it to the 5th power. So let's see. What is the square root of 4? Is it 2? And we then have a 5th power. 2 to the 5th power. If we multiplied out 5 2's, what would we get? 32. Y'all hear that? 2 times 2, 4 times 2, 8 times 2, 16 times another 2, 32. I don't know why I don't have my calculator open. But these these 8 rules we're going to be using off and on throughout the semester. For the first half of the assignments, the main ones we're going to be using are rules 3, then 5, 6, 7, 8. And before I scare you all with this, it's not as hard as it sounds. Let's start with problem 1. Okay. 6 to the 0. Do we need to write anything down for this one? No, it's a classic example of the third rule. Anything to the 0 power is 1. Sometimes students don't believe it unless they see it with a calculator. So, on this calculator, in order to enter exponents, let me clear that. There's a x squared key right here, but for anything other than x squared, it's this little carrot top. That's what we used to call it. Raised to the 0 power. Guess what it's going to say? 1. Everyone's first problem will be have the answer 1. But it can't all be that easy, so let's see about problem 2. So we're now working problem 2 in the homework.
So that would be 3 squared, which is 9.
Okay, you've got the hang of that. Okay. I've written down the problem. Now, we have a fraction raised to a negative power. So that's rule 6. To raise a fraction to a negative power, you flip the fraction. Well, when we flip the 1 over 3, we don't need to write it as 3 over 1. Just write it as 3 squared, 9. Which is 9. Okay. You're shaking your head. Well, that sort of stuff y'all need to tell me. I try to look through every test and see, but it's not easy. There's not for the teacher view of the things. We see it the way y'all see it. It doesn't say, what exactly, how, it'd be neat if they made a little thing with a table. Student answered, correct answer, that sort of thing. I'll look back at that, because I try to look through those things to see if that happens. But did y'all hear that? He typed in 4 over 1 when the answer should have been just 4, so it just counted it wrong. So things like that happen. Now, when you have a wrong answer on a test, you have to click the little red tab, and that's where it'll say student answered or your answer. For me, when I click it on the gradebook view, it says student answered. Also, to review your tests, you should be looking at the Pearson gradebook. I don't think you can get to the review using the Canvas gradebook. Next question. Number 3. It says 4 over 5. This is problem 3. 4/5 to the negative 3rd power. Four-fifths to the negative 3rd. This is using the same rule that we used on the previous one. How to raise a fraction to a negative power. You flip the fraction and drop the negative on the exponent. So 4/5 to the negative third is the same thing as 5/4 to the third. Don't say 15/12. 5 times 5 times 5. 5 times 5 is 25. Times another 5 is 125. Why did I write that equal sign twice there? All over, don't say 12. 4 times 4 times 4. 4 times 4 is 16. Times one more 4, 64. And you might want to punch that into a calculator if you doubt my arithmetic.
No, I will never doubt your arithmetic.
Oh, well, there's nothing wrong with that. So what is it? 125 over 64.
It doesn't want us to simplify it?
Oh, to write.
Evaluate.
Well, you can only, you could write it as a mixed number, but there's nothing you can divide above and below by. And algebra doesn't really lend itself well to mixed numbers. Okay? So, number 4. Let me write it down. It doesn't look like there's much to it. It says c to the negative 7. It says rewrite using a positive exponent. C to the negative 7. Let me move this down. Well, this one has a negative exponent. So we have 2 rules with negative exponents. What we're going to be using here is rule 5. We used rule 6 for problems 2 and 3. That's where it was a fraction raised to a negative power. If it's not a fraction raised to the negative power, then a negative exponent means 1 over. 1 over what? C to the 7th power. Okay? C to the negative 7th is 1 over C to the 7th. Mm-hmm. C, what did I say? 1 over C raised to the 7th power. Number 5 says write this with a negative exponent. So in algebra you always go in one direction, then you go in reverse, and that's what we're doing right now. Let me see. This is problem 5. Express it using a negative exponent. So your final answer is going to have a negative exponent. So we're basically going in reverse right here. And you know what I should have done? So far, up until this problem, I've tried to be consistent with the negative and the red 1 over. I should have put the 1 over in red. We're going backwards. So this is just going to be a 7 and a 5. What am I going to put in place of that 1 over? Yeah, right there. 7 to the negative 5th is 1 over 7 to the 5th. Any questions there? So 7 raised to the negative 5th. We're flying through here. Oh. Let's see, is there a lot of writing that we need to do on this one, or can we just type in the answer? Similar to the one we just did, it says express using a negative exponent. So what am I going to do to write it without that 1 over? It will be P raised to the, here's the exponent, P raised to what power? Yeah. See, instead of that 1 over, we make the exponent negative. Okay, so P to the negative 6. Any questions there? If you're thinking, wow, it looks like he just read the problem and wrote the answer, where's the work? Well, that's what I did. Like on the previous problem, I mean, both of these, it looks like I'm just writing down the problem and writing the answer, and that's what I'm doing. Any questions? These little negative exponents are going to follow us for the next few weeks. Okay, how does this problem differ from the other ones we've been doing? Well, let me write the problem down. It's number 7. It says, rewrite without the rational exponents and simplify if possible. We have x to the 1/5 power. Well, in the problems we've been doing, we had negative exponents. Here we have a fractional exponent. We had 2 rules about fractional exponents. Okay, so x to the 1/5. We have 2 rules about fractional exponents. Rule 7, if the exponent is in the form 1 over a number, then that's the same thing as an nth root. So for us, this is going to be, draw the symbol, the root symbol, and what little number am I going to put right here? Yeah, it's a 5th root of x, and there's nothing you can do to simplify that. 5th root of x, I'm using this property right here. A to the 1 over n is the nth root of a. Let's see. Oh, so to type this in, I click inside the box, and we've used the square root key so far this semester, but never the, this is what you use for the 5th root. You click there, and it's flashing, and that's where you put the root. I'll put a 5, and then x. Okay. Any questions? Number 8. Looks like it's the same instructions. It says rewrite without rational exponents and simplify if possible. So we have 64 to the 1/3 power.
So would that be cube root of 64?
Did y'all hear that? Let's see, right there. That 1/3, the pink 1/3 exponent is the same thing as this, cube root of 64. Now don't say 8. The square root of 64 is 8. But what's the cube root? 2 times 2 times 2. No. Is it 4? 4 times 4 is 16. Times 1 more 4, 64. So on that one, the way it says simplify if possible, you could simplify. You don't stop at cube root of 64. But on number 7, fifth root of x, there's nothing you can do to simplify that. So 4. Okay, number 9. We have 256 to the 3/4 power. I'm going to put each one of those numbers in a different color.
I forgot what it's called. Fourth root. Would that be like a quadroot?
I just say 4th root.
So give me the 4th root of 256, then that would be, the answer would be to the 3rd power.
Right, okay. Theoretically, you could do the power first and then the root, but why the heck would you want to? 256 cubed, I can't do that in my head. And then take the 4th root. I think it's always easier if you take the root first. So let me I'm writing out 4th root of 256. And then I'll cube that.
You can't see it right.
Oh, shoot. There. There. 56. I'd forgotten. 256 to the 3/4. I'll take the 4th root first because that'll get you smaller numbers, and then cube. Theoretically, you could cube and then take the 4th root. Let's see.
I wonder how you would do that in a calculator.
Okay, on this calculator here, there's a math key, but your calculator might be different.
Got a math key.
And right there they have a cube root key, number 4,
Oh, excellent.
and they also have an x root that you would use that if you had something other than a cube root. So scan down.
Would it technically be 5 though, because we're doing it by 4?
Oh, so it would be 4 to the...
Oh wait, I'm sorry. No. I need to do 5. You're right. Okay, it's a 4th root on this math. Let me see. Yeah, this is the one I need to use.
Yeah.
But I think to use that, the first thing you need to do is punch in the root. So let me clear that and go.
No.
No? You don't? Oh, okay.
It gives you the space to type it in.
Oh, it does? Okay.
Yes.
I haven't used this calculator in so many years.
It gives you the space to write it in.
Oh, let me see if that works the same way as this one.
It wants to know what X you got.
Answer.
So maybe you are...
No, I think I do have to punch in the, let me see, clear, 5,
It's
math.
Isn't it?
Oh, 4.
You need to press 4, then the math, then 5.
4, math, 5.
Yeah. What?
I mean, 256. A 4.
It's the
That's,
same answer, so...
is that right? Is 4 times 4 times 4 times 4 256? Yeah. So the 4th root of 256
And then it wants
is a 4.
4 to the 3rd power is 64.
Mm-hmm.
Which we learned in the last question.
Mm-hmm. Yeah. Mm-hmm.
This seems like it's both very easy but also very confusing at the same time.
Oh, well. Hopefully it won't be too confusing. Let's
It's
see,
not too
which one's
confusing
64?
yet. You always need to put that yet. Well, I mean, I wanted to hear what pretty much half of the thing so far. So
Let's see. Let me find.
So 49,
to the square root.
so square root of 49.
That's 7 to the 5th power.
Yeah.
Dab, dab, dab. I don't know what that was.
Y'all hear that?
It's a big number.
49
That's true.
to the
So, you know, this is
5/2 power.
Dude,
The bottom number is the root, so it's a square root of 49.
I named
well, that's really, I didn't think it was that.
And then raised to the
it.
5th.
So 7 to the 5th power.
Mm-hmm.
That's what I said.
And that's going to be 16,807.
Oh, okay. Well, okay. Catch up. 16,000 and 16,807.
807. That's a big number.
Mm-hmm. So, what did you do? You multiplied, well, I guess you put 7 to the 5th into your calculator, or you
I
could have
put
said
7
7 times 7 times 7 times 7 times 7. So, let me see. Oh,
I
wait,
like
no.
tails.
By the way, I wrote a comma in my answer, but don't type that comma in. 16,000, see what I mean? I wrote a comma there, but don't put commas in when you're typing. It might take it, it might not take it.
It might not.
You want to try it?
No,
It might not, most likely, because it would possibly think you're trying to do like coordinates.
Who wants to know the square root of 2?
Isn't that just it? I don't think you can rationalize that. Or would
What?
it be technically 2 to the half power?
okay. That's what it wants you to do. Rewrite this with rational exponents. Remember, rational is just another word for fractional.
So it's 2 to the 1/2 power.
Mm-hmm. Oh, wait. Oh, not that. Here. So the square root of 2
Equals 2 to the half power.
is just 2 to the 1/2 power.
Wait,
Okay.
I don't know why. I really want to see if you just want to make it harder on yourself. Do like 3/6. Like if it would take any 1/2 fraction, or is it only 1/2?
Oh, I'm sure it wouldn't take 3/6.
I mean, that's
Okay,
one of
but
the
simplify your
just to see.
answer. I'll see it. Since 3/6 reduces to 1/2, the question is, will it take the 3/6,
Or do you
which
have-
Jacob just made up or chose rather than 1/2? And I don't think it will.
Okay.
No.
Just testing the limits of Peterson.
1/2.
So for those people who are unsure, it has to be 1/2.
Mm-hmm.
Because like there might be some questions where it's like, what's this number to the 3/6 power? You know.
Let's see.
I
It's
know that's dumb. I'm dumb.
number 12.
19 to the 1/5.
Okay. Rewrite the 5th root of 19. There's not really any work to this particular problem. It's like the other one. You just sort of write the problem down, write the answer. The 5th root, do you all agree that's a 1/5 power? So I would go 19 raised to the
1/5 power.
1/5. This is just the same way of writing. Hundreds and hundreds of years ago, when this was all being developed, there were some people using this symbol, and other mathematicians, astrologers, so forth, the founding fathers of
The founding
modern
fathers,
algebra,
Alexander Hamilton did this.
of modern algebra, were using this notation to mean the same thing.
Who
Okay?
are the founding fathers of math?
Oh, Aristotle, all the great astrologers and so forth. Now, this is where we go from the foundations problems to the college algebra problems. So, right now, the name of this assignment is Exponential Functions, and we really haven't seen any functions yet. Okay? I'm going to define what we mean by exponential functions, and we're at problem 12 through the rest 23. This is a lengthier assignment.
Why is it 23?
Huh?
Because if it was 22, then it wouldn't be enough. And if it was 24, then it would be too
There's
much.
23 problems. No, because I took the my college algebra that doesn't have a foundations course, and I added the 12 foundation problems, and so that's how we wound up with 23. The other assignment only had 8, but that's irrelevant to y'all now. Okay, I'm going to discuss what the heck is an exponential function. Okay, an exponential function has the variable x in the exponent. An example of an exponential function would be something like this. F of x equals 6 raised to the x power. That's an exponential function. I'm going to write 3 functions here, and we're going to label them either exponential, linear, or quadratic. If we had this function, f of x equals 6x,
Isn't that like a quadratic? I don't know.
there. One of those functions is linear and one of them is quadratic.
The first one is quadratic, while the second one's linear.
Okay. By first one, you mean this one, right? Quadratic means there's got to be an x squared. This one right here is the quadratic.
No, I said that was
Linear functions have no exponents. The one that has no exponent is this 6x. So just to make sure that the terminology is clear, if there's an x squared in it, it's a quadratic function. If there's no exponents at all, like this f of x equals 6x, that's a linear function. But the new functions, new to y'all, new to this class, not new to the world of math, are the exponential functions. How do they differ? The exponent is, the variable is in the exponent. Notice on these other two, like this red x, that's the base. Everything we've seen up to this point, the variables have been, before today, the variables in the base. Now the variable is in the exponent. And that's called an exponential function. And the first thing we're going to do on problems, 13 and 14, I believe, are graph exponential functions. The graphs of an exponential function have 2 basic shapes. It's a smooth curve. One end looks horizontal. The other side starts going up real fast. So an exponential function might look like this, or it could be like this. It's a smooth curve, no peaks or valleys. One end looks like it's going straight up, and one end looks like it's flattening out. And we're going to have a couple of multiple choice graphs for these on problems 13 and 14. And I'll give you a hint. The graphs are either going to look like this one or this one.
So we know that there's no lines.
No line. In order to have a line, it would have to be a linear function.
It has to be a ramp.
If there's an x square, let's see,
So
looking at these answers here, it says graph the equation on paper. I always think that's funny instructions. And then choose the correct graph.
Would it be
What else would you be graphing it on? Well, this looks like a parabola here, doesn't it? Answer D. Let's see, can I blow that up?
no? Oh, maybe. There we go.
See, that's not the shape.
It can't.
Okay,
be
so
B
it can't be
because
that one.
It can't be B because it's a line.
Yeah, it can't be B because it's a line.
And
That
it
would be a
can't-
linear.
And it can't be C because it's pointed the wrong direction.
It's not going, it doesn't have that shape. If you're going to guess, it's got to be A, but we don't have to guess, fortunately. I didn't write the problem down. Okay, so this is problem 13. We're graphing y equals 6 to the x power. And really, all you have to do to decide what the graph looks like is just plug a few numbers in for x. Okay? Ooh, wait. What am I doing? I'm going to plug a few numbers in for x. Which number should we use? Well, now I removed what I was going to do. Like here, the graph is going from -5 to +5. So don't put anything in for x other than numbers between -5 and +5. I'm not saying you need to plug -5, -4, -3. In fact, I think that'd be overkill. But let's try plugging in a 0. Just because I want to see if y'all remember. If we put a 0 in for x, what's 6 to the 0 power? Don't say 0. It was that third rule we stated. Anything to the 0 power is 1. Okay? Let's plug another number in. Oh, that's going to get it huge. But you said 4? Okay. If we plug a 4 in for x, oh gosh, what's 216 times 6? Oops. If I multiply out 6 times 6 is 36 times 6 is 216 times one more 6 is 1296. Is that what you said? No? Oh, okay. Well, looking at the graph, notice, I was going to only plug a 1 in. That's my other point. There's the point 0, 1. But if you plug in 4, 1, 2, 3, 4, it's over 4 up 1,296. That would be the straight up part. So, have I said enough to convince you that the answer I'm going to choose is what? A. Then the next one is another one where you choose the graph. Y equals 4 to the negative x. This is number 14. Y equals 4 to the negative x power. I'm going to write it down. Well, first of all, are there some we can knock out and think that they're not going to be it? Oh gosh, where's my cursor? Oh gosh. Why don't they have touchscreen computers here? Y'all are paying enough? Don't y'all think so? Where am I missing the cursor? Someone help me out. I don't see it. Oh, I see it now. Okay. But I'm thinking it's, let's see, looking at the choices. A, that could be it.
It can't
B,
be that.
yeah.
It's too slow.
Yeah.
It can't be that.
It can't be C. Okay.
Wrong direction. Or
That
it
should
could
have.
also be D.
Might be D.
Because like the one that was like 6 to the power of x, because the x was positive and went to the, it was facing towards the left, and because this is negative, would it be the opposite, going towards the right?
I think you've got it.
Is that why you did the negative in red to associate it with the red line? Or did you just accidentally do that and I'm just...
Okay, I'm just plugging in a number. If I plug a 0 in for
Negative
x, we have 4
negative 4
to the 0. A negative 0 is just 0. I claim that that's just going to be a 1. If we put a 0 in for x, the fact that there's that negative on this one here, it doesn't matter. Negative 0 is just 0. 4 to the 0 is 1. Let's plug another number in for x. And I'm going to do something I don't normally do. I think the next number I'm going to plug in, I could either plug in a 1 or a negative 1 for x. I think it would work out easier if we plug in a negative 1 for x. Do y'all see why? What would happen if we put a negative 1 in for x? You'd have 4. We have the red negative. And now we have the green negative 1. So negative is going to be a positive.
It's just 4.
4 to the first power is just 4. I think that's enough for you to figure out which graph it is. Which one's passing through 0, 1, and through left 1, up 4. Okay, so 0, 1, that's this one here, that point. Then left 1, up 4.
Oh, it's D.
Oh. Is it D? I'm thinking it is D. It's passing through 0, 1, and then left 1, up 1, 2, 3, 4. I think this is the graph. It has the shape. For it to be an exponential function, one end should be flat. The other end, and you might think, well, it doesn't look like it's going up quite so steep. Oh, you bet it is. If you plug in a negative 5 for x, it's going to give you numbers way, way, way up there. Okay? So this is not some big, there's no sophisticated graphing technique that we use for graphing exponential functions. We just look at the graph, just plug in a few numbers and look at the graphs. Okay? Now, we're about to start solving equations. What we're about to do now is solve exponential equations using the same base technique. Solve exponential equations using the same base technique. It sounds harder than it really is. I think you already know this technique. If you had the equation 5 to the x equals 25. Could y'all tell me the solution for x?
5.
No, I was going to say, don't say 5.
2.
2.
Because I was just thinking 5 times 5 is 25.
Yeah, it's 5 squared is 25. 5 squared is 25. Y'all agree that x would be 2?
Yeah, that's where it's like kind of might confuse some people because it's like, oh, 5 times 5.
Yeah,
So
that's what you would do if it were linear. Okay, if it were 5x equals 25. But this is 5 raised to the x power. Here's what your brain did to get this answer. It thought of 25 as 5 squared, didn't it? Okay? It thought of 25 as 5 squared and then said, okay, the exponents have to be equal. And if you think that's not what your brain did, then try to solve this. 4 to the x equals 25. Could y'all solve that just by looking and thinking? You'd think to yourself, well, can I write 25 as 4 to a power? And you'd say, no. Okay? What we've just done here is called the same base technique. We solved an exponential equation. How do we know it's exponential? The variable's in the exponent. And then they had the same base. Remember, the big numbers are called bases. The little numbers are the exponents. This one right here, there wasn't a common base or same base. A good example to illustrate what we're going to be doing is, let me get this out of here. Problem 16. This is a good first example. It says solve the equation analytically. I could have said solve the equation, but instead they want you to solve it analytically. It says 3 to the 2x minus 3 power equals 9. Well, is this an exponential equation? Well, yes. The variable is in the exponent. So the way we solve these is to try to write both sides with the same base. What I'll generally do is look at the larger base, 9, and ask myself, can I rewrite that number using this base here? How could I rewrite 9 using 3 as the base? 3 to what power would give me a 9? Is it 2? 3 squared is 9? Once you have it written like this, if these big numbers, these bases are the same, the only way this can be equal is if the exponents are equal. If the bases are the same, the exponents have to be the same. If you're sitting there wondering, well, wait a minute, what if it were like this? What if there were no way we could get a common base? Then We'll use logarithms, and that's what we're working up towards in a few weeks. Okay? Y'all follow my logic here. I can rewrite 9 as 3 squared. Now these bases are the same here, so the only way they can be equal is if the exponents are equal. So now let's solve this equation here. Is this an equation we know how to solve? The purple equation I'm pointing at right here? Yeah, that's a linear equation, so move the 3 over.
So it's 2x equals 5.
Uh-huh. And then?
So divide by 2,
Uh-huh.
so it's x equals 5 over 2.
Yeah. Divide.
Or x equals 2.5.
Oh, algebra doesn't really, and Pearson doesn't usually like. Oh. The bases are the same. The exponents have to be the same. So once you get the same base, just drop those big bases and just set the two exponents equal to each other and solve the resulting linear equation. Okay? So 5 over 2. Let's see. Let's go back to number 15. 36 to the x equals 6.
Oh, would it be 1/2?
Yeah. Usually someone gets it without any sort of work. You're right.
Yeah, because it's like the opposite way would be 6 to the second power equals 36. So the opposite would be 36 to the 1/2 power.
In other words, the square root of x
1/2.
is 6. And so remember that rule about, I think we had something over here.
Let's see if you get.
Okay, yeah. Square root is the same thing as a 1/2 exponent. Okay, so the square root of 36 is equal to 6. So x would be a half. So this is one you can do sort of just by looking at it. What you're saying is the square root of 36 is, 6. And I'm wondering if this problem is always going to have
1/2.
1/2.
Yeah.
See, what about, I just said similar problem and it gave me the exact same thing.
It does that sometimes.
Yeah.
I was even going to ask you to test that out. Imagine you please have it be. Okay.
Oh, no.
That
Okay.
would be 1/3. The answer is 1/3.
I don't think so. Number 15. 81 to the x power is equal to 3. 81 to the x power equals 3. Well, darn, I wish that had been the first one rather than just 1/2. I'm going to do this problem using that same base method. I'll look at the big base and ask, can I rewrite 81 with a 3? How many 3's would I need to multiply together to get 81?
4 times.
Yeah. If you multiplied 3 times 3 times 3 times 3, that's like multiplying 9 times 9. So 3 to the 4th would give us 81. And this blue X, I'm changing the color to red. That's right there. Now what about over here? On this side, you don't really see an exponent on the 3, but we assume that what's there. If you have a number with no exponent, a 1. So we're finally about to use a rule that I stated at the beginning of this ordeal. known as class. And we hadn't actually used it. To raise one power to another, you multiply the exponents. So I'm about to rewrite this 3 to the 4th to the x as 3, multiplying those, 4x equals 3. I'll change this to a red one. Do y'all follow my logic and how I've rewritten both sides with the same base here? Common base of 3. Can I drop the 3's now? Yeah. If the bases are equal, the exponents have to be equal. So we have this equation to solve. 4x equals 1.
So x equals 1/4.
Mm-hmm.
So it would be 81 to the 1/4 equals 3.
Did y'all hear that? 1/4. 81 to the 1/4 power is equal to 3. A 1/4 exponent is a 4th root. So you're saying the 4th root of 81 is 3. What did you say, 1/4? 16 we've done. Let's do 17. Okay. It says 2 to the 5x minus, no, to the 2x minus 5 power
So that would be, or what it
equals.
So
So
what it needs to be equal to. So
this is going to show my thought process well, I think. Oops.
9/2.
Oh, okay, you've done it all in your head. Yeah, you're right. We need both sides to have the same base. So I'm going to rewrite the 16 using the smaller base. 2 to what power would give us 16? How many 2's do you have to multiply together to get 16? Y'all agree with that? 4. 2 times 2 is 4. Times a third 2 is 8. Times a fourth 2 is 16. Now, I have a lot of 2's there. Can I drop the blue 2's? 2 to a power equals 2 to a power. The only way these can be equal, since the bases are the same, the exponents have to be the same. So let's see. How would I solve this for x? I would move the 5 over. Are y'all caught up with me? And then do what? Divide by 2? So 9/2. 9/2. Let me come over here. 9/2. Y'all ready for another one? Oh, this looks terrible. Can y'all tell what this letter is right there? It's an E. And let me go ahead and write down. In math, the lowercase letter E is used to denote a number that's approximately equal to 2.718281828. It keeps going and going. It doesn't terminate. For our purposes, you're not going to use that 2.718281828. But let me write the problem down. If there's an E in the problem, that's the common base. So let me see. E to the 6x minus 1 equals, this is something you can impress people with because it looks much harder than it is, e to the 4th raised to the x power. Okay, this is number 18. E has to be the base. And we have an E as the base on both of them. But what we want to do is write it without these parentheses. What will I need to do on the right-hand side? I just want to write E to a power. The left-hand side is fine. We have E to a power. The right-hand side, I just want E to a power without those parentheses. What was that rule that told us how to get it written without parentheses? What do I do to the 4 and the x? Multiply. It's just going to be 4x. Now, are we ready to drop the black e's? The fact that the e is 2.718281828 doesn't really have any impact on it. You're not going to be doing anything with a 2.718281828. You're going to be dropping the e's now. E to a power equals e to a power. That means that since the bases are the same, the exponents have to be the same. And my battery's dead. How long has this microphone... well, can y'all hear me? The battery's completely dead. Oh, gosh. Okay. Yeah. Fortunately, there's not a lot of people in here. Oh, wow. Did I just record that? How would I go about solving this for x? It's just a linear equation. I think I'd do this. You know what? I'm going to do this. You may not like what I'm doing. I'm going to move the 4x to the left and the 1 to the right. I'm doing that to avoid any negatives. Can y'all follow what I'm doing with my arrow? 6x minus 4x would be a 2x on the left. Moving the 1 over, we just have a 1 on the right. Divide both sides by 2. Did that do it? Y'all see how I did that? The goal is to get the same base on each side without any parentheses. Oh. Okay, so I think it's the exact same. Okay, well, hopefully that happens for y'all also. 18 and 19 are just the exact same type of problem, and it generated us the same one. So, number 20. 20 is probably the best example because it's going to clearly show my thought process. Hopefully. Let me write it down. It sure looks involved. Number 20. 81 to the 3x minus 6 power equals 729 to the x plus 4 power. Oh, this is a good problem. See, I've written it down. Let me make sure I didn't miscopy it. 81 to the 3x minus 6 equals 729 to the x plus 4. Okay. My first thought is, darn, too bad there's not an E in it. Because if there's an E in it, then that's the common base. But My second thought is, okay, look at the large base. Can I multiply 81s together to get 729? If I start multiplying 81s together, can I rewrite? I start multiplying 81. Like, is 81 squared 729? It's not, is it? Okay. So we can't write 729 using an 81 as the base. So now start working with the small base. How can I rewrite 81 as some number to a power? There's something in the multiplication tables. What number squared gives 81? 9? Let's write 81 as 9 squared. Now let's come over here and try to write 729 as 9 to a power. I'm just going to start multiplying 9s together until we get 729. 9 times 9 is 81. What's 81 times 9? 729. Again, these are all rigged out to have a common base. So I'm going to rewrite the 729 as 9 cubed. I'm rewriting the 81 as 9 squared. And if you're thinking, well, wait a minute, what if there isn't a common base? We'll answer that eventually, but not today. It'll be after we do our logarithm discussion. To raise one power to another, you have to multiply those. And when we multiply, we have to distribute. So the exponent on the left is 6x minus 12. Having seen that, can y'all tell me the exponent we're going to have on the right? 3x plus 12. Am I ready to drop the black 9s?
Yes.
Yeah. The bases are the same, so the exponents have to be the same. So this is a linear equation. In order to solve it, I'm going to put all the x's onto the left. I think I'll move the numbers on the right. Is it clear what I'm doing with those arrows? 6x minus 3x would give us a 3x on the left. Don't say 0. What are we going to have on the right? Can I move this 12 over? 24? And now divide by 3. X equals, yep. X, the solution set is 8. Oh, there's only 3 left of these. Okay, there it is. Okay, so I rewrote 81 as 9 squared, and I rewrote 729 as 9 cubed. If you're wondering, well, what if instead of 729 it had just been 7? We'll be able to solve these things using logarithms when there's not a common base very nicely in a few weeks. Okay? I always think I want to start the semester with logarithms just so right off students learn something that they've never done before. We ready to go on?
Yep.
Mm-hmm. Just 3 more. You can handle it, okay? Oh, wow. And then you see this problem, 21. It's not as bad as it looks because unlike problem 20, where you had to figure out the common base, there's no doubt what the common base is on 21. If you see an e in the problem, that's the common base. So let me write it down. 1 over e to the negative x equals 1 over e to the 4th raised to the x plus 7 power. Okay, I checked to make sure I copied it correctly. Maybe I'm paranoid about that, but having done this for so many years, there's so many times students' only mistake is they wrote the problem down wrong. Okay. Unlike number 20, where we had to figure out the common base was 9, on this problem, there's no doubt. The common base is, if there's an e in the problem, the common base is e. It might be easier to see this if we start with the right-hand side. Let's write 1 over e to the 4th without the 1 over. What will I have to do to that 4 to get rid of that 1 over? That's right here what we were doing earlier. If you have a 1 over to get rid of it, you make the exponent negative. Okay? The way this stuff just builds slowly, one on top of the other. Okay, what we were doing here, to get rid of a 1 over, you make the exponent negative. So I claim this 1 over e to the 4th, I'm going to write as a e to the negative 4th raised to the x plus 7 power. I'm trying to write both sides with just an e. Okay? An e and an exponent. In a moment I'll get rid of these parentheses by multiplying this stuff. But what about over here? You might think, well, wait a minute, it doesn't have an exponent on the e. And I'm going to say, sure it does. If you don't see an exponent on a letter or on a number, there's always a 1 exponent there that isn't written. Having said that, how am I going to write it? It's going to, without the 1 over. I'll have e, and what am I going to put in front of this black 1? How am I going to write it without the 1 over?
Negative?
Yeah, make the exponent negative. Now we're ready to get rid of the parentheses. We're just going to have e equals e with no parentheses. To get rid of the parentheses, you multiply the exponents. Negative 1 times negative x, that's just going to be an x there.
And then it's going to be negative 4x minus 28.
Did y'all hear that? Negative 4x minus 28. And am I going to write down any more e's on this problem? No. The bases are the same, the exponents have to be the same. So we just write it. Drop the e's. And get that x by itself. What can we do here? I'm going to add 4 to both sides. So 1x plus 4x, is that going to be a... Yeah.
Equals negative 28.
Negative 28.
And get x by itself, divide both sides by 5. So it's x equals negative 28 over 5.
Divide by 5, so we get x equals negative 28 over 5. Okay. This one is, these two I've done here, 20 and 21, they're some of the most involved problems. Hopefully you're following the logic. If the bases are the same, the exponents have to be the same. If you're wondering, well, wait a minute, what if there is no common base? We'll handle that later. Y'all ready for me to punch in negative 28 over 5?
Yeah, but it's about everything.
Negative 28 over 5. And even though that seems sort of bad, but you know the common base. If there's an E in it, it has to be the common base. Okay, let's see, 22, 23. Okay, the last two are going to have some square roots in them, it looks like. And then we'll be done. Number 22.
X equals
The square root of 2 raised to the x plus 4 power equals 16 to the x power.
So would it be negative?
Oh, you're already getting to the answer. First of all, what would the common base be? Well, it's got to be a 2. There's nothing else. You can't rewrite 2 as any number to a power. But we have the 2, and then using something that we did earlier, how can I rewrite it without that square root? A square root is a 1/2 exponent.
So x equals negative 3 then. Because negative 3 plus 4 is 1. So
Okay, let me finish writing this. You've gotten ahead of me. So 2 is going to be my common base. I'm going to rewrite 16 with a base of 2. How many 2's do I need to multiply together to get 16? I was going to say don't say 8, and you didn't say 8. You said 4, and that's exactly right. 2 times 2 is 4, times 2 is 8, times another 2 is 16. And now we need to write it without the 2's. Normally, what I'll do is distribute every time we've gotten rid of the parentheses, but for this particular problem, because of the fraction, look at how I'm going to write it. I think it works out easier this way. Just to say 1/2 times x plus 4 equals, I'll multiply those together to get 4x. If you want to distribute the 1/2, okay, but writing it like this, you can get this 1/2 to cancel real easily just by multiplying both sides by 2. We just multiply by 2. All of that fraction cancels out, and all we're left with on the right-hand side is x plus 4. No, on the left-hand side is x plus 4. And what do we have on the right? The 4x times 2. Is this all just hitting you in the face and bouncing off now? We're about finished. The 4x times 2 is 8x. You'll see how I went from here down to here? I think multiplying by 2 to get rid of that fraction is easier than distributing the 1/2. Let me see. How about this? 8x minus 1x is 7x.
Divide by 7
Mhm.
on both sides, so it's 4 over x to the 4.
Yeah, divide by 7 on both sides to get 4 over 7. This is why the videos are sort of better than in person. On the videos, you can just pause me or stop me for a while. But in person, I got to keep going. So 4 over 7. If it's just... And there's another one just like that. Do I need to show look back over here first? Oops. Everyone get that written down? So go into... And now one more problem like that. Number 23. This is the last one. The square root of 3. The square root of 3 raised to the x plus 5 power equals 81 to the x power. I like these problems paired like this where they're so similar, just so hopefully you'll see that there is a pattern on these. Here, what's the common base going to be? 3? Let me move it up. So I'll start off rewriting the square root of 3 as 3 to 1/2. And that's really the hardest part of the problem. For 81, how many 3's do you have to multiply together to get 81? Is it 4? Let's multiply our 3's together. 4? 3 times 3 times 3 times 3. That's sort of like multiplying 9 times 9. When you multiply, well, that's an incredibly stupid statement of mine. It's not sort of like multiplying 9 times 9. It's exactly like multiplying 9 times 9. So this problem is sort of similar to this one, right? Now let's write it without the big 3's. And don't distribute the 1/2. Just write 1/2 times x plus 5 equals 4x. You begin to see why it's much better to do what I'm doing here rather than distributing. If you distribute the 1/2, you're going to wind up with 2 fractions. So multiply both sides by 2. And we have x plus 5 equals 8x. Subtract the x. You get 7x on the right and 5 on the left. Divide both sides by 7. 5 over 7. This is a lengthy assignment, but at least I made it through. I don't know if y'all made it through, okay? But 5 over 7.
No, we didn't make it through this. Actually, all of us have
Well, if your brain didn't make it through following all of this, I'll post the video in a little bit, and you can look back over it. I know it's sort of bad. I was joking as I said, you know, you can't pause me in person. The videos you can stop and come back to, okay? So, if you have any questions, I'll be glad to try to answer them. Otherwise, I'll see y'all on Thursday. Generally, students like the next assignment.